This is going to be a super short lesson because there's not too much to say about it. There's also something called carbon NMR. It's like proton NMR, but it looks for carbons instead of protons. It is a helpful spectroscopic technique, but not as helpful as proton NMR if you want my opinion. So it works just like HNMR. But visualizes carbon instead. And specifically, it visualizes C13. Carbon-12 is NMR silent, so you can't actually see carbon-12, but you can see carbon-13. So we can just mention that carbon-12 is the normal, the most common form of carbon. Call that an isotope. But it's NMR silent. It's invisible by NMR, so C13 is used. Unfortunately, carbon-13 is only 1.1% abundant. And the effect is that we have a lot longer acquisition time. It takes about 10 minutes to take a carbon NMR spectrum versus about 1 minute for a regular proton NMR. So much longer acquisition time. And there's a lot of noise because you have to really turn up the receiver gain very high to basically you're turning up the volume really high to try and listen to the song that's sung by these carbons, which are pretty rare. And because we have to turn up the volume so high, we hear a lot of noise. We hear a lot of static in the background. So when you look at some carbon NMR spectrums, and I'll show you some of those, you're going to see a lot of noise. A lot of, looks like grass at the bottom of the spectrum. Now, the nice thing about carbon NMR is you don't have to worry about coupling or integrations. So coupling, that is like doublets, triplets, there's none of that. Everything's a singlet in carbon NMR. And there's no integrations either. So we don't measure the area under the curve for carbon NMR. So really all we're looking at is the number of signals and the ppm. That is the position of the signals along the x-axis. So let's take a look at an example of a compound. How about this guy here? Beautiful compound. Now, how many signals would you expect to see in the carbon NMR? How many signals would we expect to see? Well, how many different carbons are there in this molecule? And keep in mind their symmetry. So the two carbons on the left and right, those are the same. So we'll just call that carbon C. Then these two carbons are the same, carbon B, and then there's one more carbon right here in the middle that's obviously unique. And that will be carbon A, sorry. So we have 3 signals in the carbon NMR, 3 unique carbons. B and B are the same, and C are the same due to symmetry. So 3 signals. How about in the proton NMR, just for practice? Signals in 1H NMR. How many different types of protons are there in this molecule? Well, there's the methyl group protons, those are the same. And then there's the methylene protons, those are the same. There's no protons on carbon A. So that means there's just 2 signals. And we did an example, actually I think we did this exact example in the previous lesson. So just watch that previous video to see the proton signals for that molecule. Okay, now the carbon x-axis for carbon NMR is a lot larger than the x-axis for proton NMR. So if we draw our x-axis here, instead of ranging from 0 to 10, carbon NMR goes from like 0 to 200. Okay. 0 is where TMS, which is the standard, appears, tetramethylsilane. And then let's just draw in some numbers here. We'll draw 20, 50, 90, about a 140, 170. Okay, these are some approximate values that'll be helpful. So the alkanes, the typical carbons that are just single bonded carbon, sp3 hybridized carbons, those show up around 0 to 20. Something near a double bond could be between 20 and 50. So near double bond. That's like allylic carbons, carbons that are near double bonds. Carbons that are next to a heteroatom, like oxygen, nitrogen, or a halogen, appear between 50 and 90. Okay. Alkene carbons and also carbons that are part of aromatic rings show up between 90 and 140. So we call it alkene carbons and aryl carbons. Those are carbons in part of an aromatic ring. Between 140 and 170, we have the carbons of esters and amides. So like if you see a signal around, say, like 150, most likely that is the carbon, the CO double bond carbon of an ester or an amide. And then above 170, like up till almost 220, you have the carbons of aldehydes and ketones. So like, for example, the central carbon of acetone, that carbon will appear around 200. Okay, so for example, carbon A would appear around 200. Carbons B, those are near double bonds, so those might show up around like 30. And then carbon C, those are just alkanes, so those will show up around 10. All right, let's do a couple example problems just together, and then that'll be the end of the lesson. So that's all you basically need to know about carbon NMR. Okay, so here are some example problems. Let me go ahead and zoom in here. And so the first question just asks you to predict the number of signals in the carbon NMR. And this is basically just a symmetry game. We just want to figure out the symmetric carbons. And so try and find a plane of symmetry. That's helpful here. So I'm going to see like compound A. I can see there's a plane of symmetry that kind of goes right down the middle here. And so what that means is that this carbon is going to be unique. 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 And then they're reflected onto the other side. So this would have 4 unique carbons because I see that these two are the same, these two are the same, these two are the same, and these two are the same. So we'd have 4 signals. I'm not going to write in green. That's hard to read. Let's try B. Again, I'm going to draw a little plane of symmetry here, right where I see it, and then just look at each half. 1 carbon here, 2, 3, 4, 5 unique signals on the right half of that molecule. So that's going to be another 5 signals on the left side, but they're equivalent to each other. Okay, so 5 signals. All right, C, where's the plane of symmetry in C? Well, let's see. It looks like the plane of symmetry just goes right down here. Okay, so obviously the carbons on the end are going to be unique. Let's try a different way of doing it. Let's do highlighter. Okay, so these 2 carbons are the same. These 2 carbons are the same. And then all 4 carbons inside, like the other remaining carbons, are all the same. 1, 2, 3, 4, because of symmetry. So this is a total of 4 signals. All right, I'll let you try and figure out D on your own. Try and figure out what are the number of signals that you would expect to see from this compound. I'll give you a hint. The answer is 4. So see if you can figure out why there's 4 signals from D. Okay, 2 is a little bit like 1, but a little bit harder. It says predict the number of signals in the carbon NMR and the chemical shift for each signal in the following compounds. Okay, let's start in the middle and work our way out. So obviously, this carbon in the middle is unique. It's the carbonyl carbon. But then moving out from that, we have 2 equivalent carbons. These 2 are the same because of symmetry. And then we have these 2 are the same because of symmetry. But the 2 methyl groups are not the same because one is cis with the CO double bond and one is trans with the CO double bond. So they are similar but slightly different. So we'll call this top one orange, and the bottom one will be green. So those two are slightly different. Okay, because the double bond there, this double bond here, prevents rotation, making it so that those two methyl groups can't interchange by rotating. So this is a different methyl group than that because one is cis and one is trans with the double bond. Okay, so now let's go ahead and predict the relative chemical shifts of all of these signals. Okay, so right in the middle here, we have a ketone. So that is going to be 200. Let me go a little bit thinner pen. So ketones show up around 200. And if you remember double bonds, those show up around 120 to 140. So why don't I make these 120? And I'll just make these a little bit different because they're a little bit different. I'll make them 130. Again, as long as you assigned a value between 120 and 140, I would give you full credit. And then the methyl groups on the end here, these guys, these are sort of near double bond. So remember, those show up between 20 and 50. So why don't we just call these 40, choosing at random. And then these guys are similar to the orange, just slightly different. Why don't I call those 42? Again, if you had said 50, I would have given full credit. It's okay. You don't have to be exact. Okay, let's try B. This is obviously a unique carbon. This is a unique carbon. This is a unique carbon. And then these two methyl groups are the same. There's no double bond here, so they can freely rotate around the bond and interchange those two positions. So those are the same. Now let's go ahead and assign some chemical shifts. We have the aldehyde carbon. That's going to be around 200. We saw that already. This one is near a double bond, so why don't we call that 40? And then the rest of these are all alkanes, nothing special about them, so we can just call this one 20. And why don't we call both of these guys 10? All right, I'll let you figure out C and D on your own. And let's move on to number 3. This one's really fun. It says draw the carbon NMR for the following compound. Okay, we're going to draw this compound. Okay, so first thing I notice, what I'd like to do is kind of assign how many signals I expect to see. And so let's go ahead and assign a color for each unique carbon. Okay, so I'll start on the right side. And obviously we have a unique carbon here. We have a unique carbon here. And we have a unique carbon here. We're not going to count the oxygens because they're not carbons. This carbon right here is unique, but on either side, they are equivalent because of symmetry. And as we move one down, those are different than the purples, but they are also equal to each other. And then we have one more kind of unique-ish carbon over here. We'll do that one in red or like dark brown. And so we expect to see 1, 2, 3, 4, 5, 6, 7 different signals. So let's go ahead and draw in those 7 signals. The one that really stands out to me is the green one, part of the ester. We know that that shows up around 160. Why don't I just label it on here? So this will be 160, where the ester shows up. This carbon here is next to an oxygen. Remember, if it's next to an oxygen, that shows up between 50 and 90. So why don't we just call this 70? And then this guy over here is just alkane. So that's between 0 and 20. We'll just call it 15. Okay, now we have a bunch of carbons that are part of a benzene ring. Those show up between 120 and 140. So why don't we make this one 120? We'll make the purple ones 125. Just make them a little bit different. They're all in that range. The blue ones, we'll make those 130. And the red one, we'll make that 135. Doesn't matter. As long as it's all between 120 and 140, I'll give you full credit. Okay, so now let's draw in those signals. So we have one signal at 15. Whoop. We have a signal at 70. They're all singlets, remember. We have something at 160. The ester. Let's see. We have a peak at 120. We have 2 carbons contributing to a peak at 125. So why don't we make that double height, just to show that there's 2 carbons contributing to that peak. Then we have, let's see, 2 carbons at 130. We'll also make that double height. And then we have one at 135, so we'll make that small again. And now we just want to check and confirm that we have 7 signals. 1, 2, 3, 4, 5, 6, 7. And that's our carbon NMR. We just drew a carbon NMR. Pretty cool, right? All right, great. Well, that's all there is to know about carbon NMR. So now just whip out the handout, the worksheet, and answer the questions. Turn in your answers, and you're all done with this lab. Now you should know all there is to know, for at least for this class, for proton NMR and carbon NMR. All right, have a good day.